You do have this in your handout. But let's do a Mankova now, everybody. Let's have exercise, diet, and health maintenance. And let's control for the same covariance. And let's look at the between group differences, relationship versus non-relationship, and control for number of hours of exercise. So as you can see by the syntax, we've got the DVs, we've got your fixed factor, and the width always means there's a covariant. Always means there's a covariant. So now, again, here you have exercise, diet, health, maintenance, and are you in a relationship? You can see the means are higher for those on exercise, diet, but for health maintenance, interestingly, those not in a relationship actually have a higher mean. So again, always focus on the means, everybody, or not focus, but describe it. How did we do on the homogeneity variance covariance matrix?
Happy.
Yes, 0.372. So we're okay. And now you have a lot of variance covariance matrices. I mean, you have three DVs, 2 groups. And here's your multivariate test, everybody. As we see, there is a significant relationship of the covariate and the linear combination of the DVs. The linear combinations. 19.7% of the variance is accounted for.
That's not a lot.
19.7 is pretty good. 19.7? That's a lot, 20%. I mean, yeah, relative to having 60 or 70, but in applied research, 20% is pretty darn good. Here we see what the actual fixed factor is not significant, 0.499, and this is a small effect size. 1.7% of the variability in the linear combination of DVs is due to between group differences when controlling for the number of hours of exercise. When controlling for the covariate. Don't forget that part, everybody. Think of it akin to a partial correlation. So there we see that even though we may have had a reduction in error, and it's always good to do the MANOVA and the MANCOVA. Compare it to the MANOVA and see if it changed very much. See if we get much of a reduction in the error. Right, again, looking at the error, there's the intercept demo, looking at the error variance, there's the error degrees of freedom, and see if the error has changed very much. How do we do on the univariate homogeneity of variance assumptions? All of them are not significant. So we've done good there. And here's your one-way ANCOVAs. Here's your one-way ANCOVAs, everybody. So there we see, looking at demo 5, which is if you're in a relationship or not, none of them are significant. None of them are significant. We don't see any between group differences. Even though the means are higher for exercise and diet in those in a relationship, none of them are significant. Effect sizes are all pretty small. 1.4% is the biggest effect size.
So that means with the covariate doesn't have an effect on the linear combination of DVs?
No, the covariate does. Look, it's significant for all outcomes.
Oh, demo 3 is the covariate.
What it means is there's not a between group difference when controlling for the covariate. Don't confuse that. This is the covariate relation. This is the number of hours of exercise, and it is significantly related to each of the individual outcomes. But this variable is your fixed factor, demo 5, and it is not significant. So make sure in the output, everybody, not to confuse your covariate and your grouping variable. And here are the adjusted means, everybody, for all 3 outcomes based on that formula. Again, all of these are evaluated at the mean of the covariate, and these are all adjusted means. These are all adjusted means. And remember, the MANCOVA is ultimately done on the adjusted means, not the raw means. That's what's ultimately done. And that's why sometimes you can gain some power, everybody. So that's the MANCOVA. Really, not that different from the ANCOVA that we've gone over. Now, a couple of points, everybody. How do you test the homogeneity regression assumption? With one covariate, it's really easy. You just create a product term under the design syntax, or as I showed you earlier, if you go into the model option in SPSS, put in the main effects and the interaction. Don't forget the main effects. Main effects and interaction. You just run this once. You just run this once, everybody. And here it is. Here's your multivariate test of the interaction. Here's the multivariate test of the interaction. Unfortunately, we have a p of 0.013. Usually we've been pretty lucky throughout the semester. Well, guess what? Our luck is ran dry. So Zach did ask earlier, well, what if it is violated? There are, some people would say that it's inappropriate to use the covariate because it interacts with the IV. Some people use things like, well, don't worry, MANOVA is robust to these violations. So it just does mean that maybe it's not appropriate to use it as a covariate because you need to take into account that it does interact with the IV. The IV does not have equal slopes on the linear combination of the outcomes. Remember, we have 3 DVs. So we do have significance there, everybody. We do have significance. And let's look at individually, because this might help us ferret out where the problem is. Exercise.
Ferreting.
Does everybody see the p-value of 0.01 for exercise? So sometimes that's why the univariate can shed insight into when things don't all go right for the multivariate output. You can see, oh, guess what? Something's going on with exercise. So you may want to examine exercise and see what the heck is going on there. See how the slopes are different. And that may help you, everybody. And here, I did it for you. There it is. Remember doing these types of graphs, everybody, in 602.2 when we looked at interaction of categorical and continuous variables? And you could do these types of plots. And here you can see how many hours do you exercise a week, the covariate, and the DV is exercise. And we see those in a relationship have a stronger relationship than those that do not, 25% versus 20%. And there's kind of a crossing, right? A crossing at low levels of exercise. Do you see visually the nature of the interaction? There you go. So there's something going on that...
Now what would you say?
I'm trying to think. So those
who are who don't exercise but are single at really low levels, maybe they're just so out of shape they can't find a relationship to be in.
And then...
But then as you work out more, as you are in a relationship, fitness goes down because you get in that comfort zone.
I think that's a good explanation. I don't know if it's true or not, but on paper it sounds good. That might be, right? It's not always easy to explain why that might be the case. And sometimes, if you really want to find it out, you may want to look at other variables, right? And try to see what's going on.
Because when 2 variables interact, that means that one has an impact on the direction.
And not only the impact direction, but it means it violates that we want to have equal slopes on the covariate DV. We don't expect the slopes to have the same we don't expect the same intercepts,
right? Because
the means may be rather different. But for this statistical tool, it kind of assumes that the slopes are equal and there's a linear relation. It's polynomial and there's an interaction. Then it means you got potentially inflated type 1 or type 2 error, and your coefficient, your parameter estimates may be biased. So here in Zach's explanation, that's a viable explanation of this. Okay, let's add a second covariate for the first time in this class. Let's add a second covariate. Age. Okay. Here you can see hours has a pretty nice relationship with exercise. And kind of smalls with diet, kind of smalls with health maintenance. 0.076, 0.18, 0.1. What do you think about covariate of age with the 3 DVs? Does that look like a nice relationship or not really, in your opinion? 0.076, 0.18, 0.11. Not really. Do you think that covariate's going to help us or maybe even potentially hinder us?
I don't think it's going to help.
It's not going to help, and if anything, if it's got a substantive relationship with hours exercise, there's going to be a problem with intercorrelation of covariates. And do you recall that you get a degree of freedom sucked away from the error term each time you have a new covariate? Here it takes away 1 degree of freedom, and now it takes away 2.
And that's probably because it increases type 1 error.
Potentially, actually, if anything, it'll increase type 2.
Type 2.
Yeah, it'll do the opposite. We would love to have a minimal intercorrelation of the covariates. How do we do? We would love a minimal negative 0.053. Does that seem pretty small?
Yeah.
Yeah, so that's good. That's good. That's a small intercovariate. So now let's put in two covariates for a Mancova. Let's do a Mancova with two covariates. And we can see here, demo 5 is still our fixed factor. In a relationship versus not, we still don't have significance. With hours exercise, still significant, but look at age. So guess what? Do you see, everybody, that age is not significant?
Yes.
As a covariate on the linear combination of the outcomes. 3.7% of the variability in the linear combination of the outcomes is attributable due to age, compared to 20% for hours exercise. So you got yourself a covariate that, if anything, may compromise the power of your study. Again, think of it this way. If my mean square error equals 120 for ANOVA, and it's 120 for ANCOVA, and my degrees of freedom is 19 for ANOVA and 18 for the ANCOVA, because it sucks away degrees of freedom, relatively speaking, look, our error term is going to be larger with the covariate. Because think about it. You have a denominator that's a bigger value. So again, everybody, if you have a lousy covariate, and I've been on more than a few studies that have pretty small correlations, you're actually going to start to add some problems to your study. So let's look here, everybody, if we have significance anywhere. Let's look at the ANCOVAs. So now this is the ANCOVAs, and we can see none of it is significant. We see, again, for hours exercise, significant, and only for diet is there a significant relationship of age, the covariate. Only for diet. So these are kind of similar to what you would get in regression analysis, because this is continuous with continuous. And here's the adjusted means based on the two covariates. It adjusts based on the mean of exercise and age. So there it is. These are the adjusted means that are ultimately analyzed. So that's a Mancova, everybody, with two covariates. But things get a little trickier on the side of assumptions, which is why for the homework and the test, I'm only going to have you do one covariate. But I do want you to be exposed to what happens with testing the assumption. For one covariate, you have the assumption of homogeneity regression, which tested the interaction of what, everybody? Homogeneity regression tested the interaction of what?
The covariates.
The what? The what and the what? The interaction of the
Covariates and the deep.
and the IV. Covariate and the IV. The DV is a DV. Right? Remember, don't forget, Jocelyn, that you're looking at the interaction of the covariate and your IV.
On X group.
But what if you have two covariates, everybody? Then you have this fancy thing called parallel regression planes.
Ooh.
And then Zach, being the adventurous type, decides to have three covariates for leadership. He does their age, their income, and number of years management. So Zach will learn about this thing called homogeneous hyperplanes.
Really?
That just sounds awesome.
Today's not the day.
Think about it.
I'm going to flood my hyperplane to the centroid.
This is getting very Gamma Jim. It does sound very Star Trek-y, doesn't it? But I mean, think of a
To rescue
hyperplane.
you with two parallel regression planes.
Yeah, it's two parallel regression, but think of a hyperplane.
Think of it.
Yeah, like visualizing, right? The kind of the three-dimension aspect of it.
Oh.
So, I'm sure there's a way to test these two assumptions in GLM, but I haven't figured out a way. And I went on SPSS listserv more than a few years ago, and no one gave me an answer. So there's probably a way that I'm naive to. I could find a way to test the assumption.
You find it.
I did in
Called
MANOVA.
the
I
Glaser.
did in MANOVA. I did find the way. In the GLM, I haven't. So in MANOVA, everybody, which is syntax only, exercise, diet, nutrition, my demo 5 with the two demos, look what I did on the design matrix. I added the covariates. I pooled them together. Then here's the demo 5, demo 3 by demo 5, plus demo 7 by demo 5. In other words, remember, this is your fixed factor, everybody. This is your fixed factor. So, guess what? I pooled together both interactions. I pooled them together, the interactions. And there you go. There you go, from the old mainframe output, and it's significant. Here it is, demo by, here's the IV by covariate 1, IV by covariate 2, and we got significance. And specifically, we got significance for exercise.
And that means that what?
So well, this is we're using Zach's wonderful description there about, but now we got to add not only exercise, we got to add the other variable, age, because we have 2 covariates. So it means that guess what? There's now we're talking about parallel lines. So you got 2 covariates. So it's almost as if, I've never had to draw this before, and the book definitely doesn't. But now we've got not only x1, but we've also got an x2. So it's almost like you'd have, and remember it's a linear combination of the dv's. So it's almost like you'd have male, female, and superimpose an x1 and an x2. So you'd have to simultaneously impose 3 dv's, 1 IV, and 2 covariates. Visually, if you want to examine what the heck's going on. I would just probably look at the means and try to make sense of it. So that's how you do it, everybody. Now, Zach, being the kind of guy he is, wants to have 3 covariates. IV times covariate 1, plus IV times covariate 2, plus IV times covariate 3, in MANOVA syntax. So you can test the assumption of homogeneous hyperplanes. I have not found a way to do it in the GLM. I'm sure there's a way to do it, and I played around with this for a while using programming language. I couldn't replicate what I do in MANOVA. But so you can test that assumption, everybody. You can test the assumption. So I just want you to know about it. I will not be giving you this for homework or the take-home. But if you do have 2 or 3 covariates, there is a way of testing the assumption using a MANOVA interface. Now, what if you have linearity? There's a linear relation, but the regression slopes are not homogeneous. There is what's called the Johnson-Neyman technique, which I mentioned earlier. Look at the classic article, ANCOVA for non-parallel slopes. So, here's kind of the article. And it is possible. I have found, and I introduced this to you in 602.1. No, I'm not sure. It's in 602.1 notes now. I'm not sure if you got it or not. But there is a software called Process, a free one on the web. And there's actually a way to get the Johnson-Neyman technique to see exactly the regions of significance. In other words, I'll do it over here. Let's say you have something like this. Right? It's probably not significant there, but you see there are certain regions of significance where there's more of a non-overlap. Almost like an inflection point is here where it turns. The Johnson-Neyman technique will actually test that for significance. And in the process program, it can really help you find this if you're interested. And actually, I started playing around with this. Process and Johnson-Neyman technique. Remember that guy? Oh, Hayes. This is a great little download, everybody. And I know I introduced it to you already in 602.1, 602.2. He's done a lot of work in applied research. And this process program right there, does mediation moderation. And there's a new book I just ordered. I just ordered it last week. It'll be in April. It's called Introduction to Mediation Moderation and Conditional Process Analysis. It's a wonderful book that'll help reflect this software that can look at interactions, areas of significance in the interaction, moderated mediators, mediated moderators. Really nice SPSS macro, where you don't have to use the structure equation modeling software. And so I'm having a lot of students use that. Anarchy test this. Johnson-Neyman technique. Now what about power and ANCOVA? Well, guess what? You got to know how much of the variance you anticipate the covariate will share with the DV. You have to put that information in, everybody. So if I have two groups, and this is using power precision, certain power, you have to know how much the adjusted R square is for the covariate. Is it 3%, 5%? You have to kind of give an idea. So here, what if I had a study with two covariates, and I think they account for 10% of the variance? And if I have a small effect size, I'm going to need 788 cases, 394 people. Or G-power. This is free. As you know, I've talked about G-power. G-power will do the same. What if I have a medium effect size, everybody? A medium effect size of 0.25, alpha 0.05 power, 3 groups, 2 covariates, but I have a medium effect size, I need 442. So, again, you will need to have an idea of what your R squared is to do a power analysis for an ANCOVA. And for your homework, you're going to go ahead and do a ANCOVA. Do next week. You're going to, number one, check the relationship of the covariate and DVs, right? Just look at the correlation. You're going to look at the linearity of the covariate and the DVs. So you'll do a plot of each of those, of each covariate and DVs. You're going to test the assumption of homogeneity regression, IV by covariate interaction. And I've shown you how to do that today. You're going to run a ANCOVA, run the full factorial, and summarize. And also, just run the MANOVA to compare if you had much gain in power by incorporating the covariates. It's a nice comparison to the MANOVA and the MANCOVA just to see if power increased, did the R squared change very much. Also, examine the adjusted means and see if you think there's much of a difference from the unadjusted means. So for this, everybody, your IV will be sex, your DV will be health and environment, which is 2 DVs, and your covariate will be item number 24, overall rating of quality of life. So that is your homework. Due next week to do the ANCOVA. Just 2 groups, no 2-key, no post hoc, just 2 groups. Male and female, keep it nice and easy, no interactions. And you can get fancier. You can start adding interactions and everything else. We'll keep it nice and simple. But do look at all the assumptions. Don't forget, everybody, once you run the assumption for homogeneity of regression, right? Once you've ran the model, you put in custom, you put that in, you put that in, right? And you put in the interaction, right? You do all that in the interaction. This will test homogeneity of regression. Don't forget to rerun it and go back to full factorial. Don't, right? Get rid of that interaction term. Any questions then about the homework? That's due next week. You guys good?
Do we have 2 more homework assignments, including the one due next week?
I'm not sure. 1 or 2.
1 or 2?
1 or 2. Because then you have the take-home and the SEM. I know I'm definitely going to give you an EFA homework.
Okay.
I know that. There's a chance I'll do repeated measures homework. Awesome. Awesome. Logistic regression, that'll probably be just part of the take-home.
Okay.
And you're going to be comparing that to discriminant function analysis. Okay, everybody.
Okay.
Let's move on. Some of you may decide to create an instrument for your dissertation. You may decide. What's that?
Dr. Nguyen told us not to do that.
Dr. who?
Nguyen?
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 She suggested not to. That doesn't mean you can't.
Dawn?
Okay.
I don't think her name has always been Nguyen.
Okay, Dawn Ferguson? Is that?
Yeah.
Okay. Okay.
She's our psychometrics.
Okay. Why did she indicate not to?
Didn't she do it? And
I think she was talking more about creating an instrument for as part of your study, not as it being your entire dissertation.
Okay.
So she meant like don't create an instrument to look at something else. Like if you're talking more about creating just an instrument as your dissertation, right?
It depends.
Yeah.
Sometimes it's part of a research question. So you want to go ahead and you have, let's just say, a basic regression model or a multivariate regression with multiple outcomes. And you want to predict a brand new construct called organizational depression. Just depression of an organization, so that's a people. Let's just say you just kind of have each of you have a perception about how depressed you are on the job. And there's no scale out there. There's tons of depression inventories, but nothing that's geared for depression on the job. Let's say there's nothing even close. But you also have a research question that includes covariance, predictors, interactions, moderators, mediators, or maybe you want to do structured equation modeling, get really fancy. And then you got to create the tool for your dissertation. So there could a dissertation in it. So you basically have two dissertations in one. You have a strong psychometric part of your dissertation, and then you have the part that's answering your substantive research questions. And that adds a lot of work. And I've had a few students that have done that through the years. It'd be great, ideally everybody, it'd be great to find an instrument that's off the shelf, already validated. And I assume you've gone through validity and reliability or psychometric class, the construct validity, predictive, all those. And we don't call it validity of a test. It's not validity of a test. It's not reliability of a test. It's the validity from the inference made based on the score. And I hope that differentiation has been made. It's an inference made on a score. They no longer use terms. In fact, people who still say validity of a test, that's wrong. That's wrong nomenclature. And the APA and the AERA have made that very clear. Even go in the book on the APA, Standards Educational Testing, it's not validity of a test. It's evidences that you're accumulating about an inference made on a score. That's what ultimately is being validated. So, that being said, you decide as your dissertation, as Zach was saying, either in part you're going to just create an instrument, which is a huge effort in itself, because you got to go through item creation, item validation. You got to go through maybe subject matter experts to get all the items. You probably need to do a pilot. Then you need to get the real sample, which has to be a fairly large sample size, contingent on a number of items. It's a lot of work to create an instrument. So yeah, absolutely, I agree with Don. Absolutely. If you can't avoid it, try not to. If your research question includes an instrument you're going to have to create, you have no choice but to do two parts. Psychometric, because there's no way anyone's going to allow you, or I'm not going to allow you, to create an instrument as part of your research question for your MANOVA or regression and not validated. And reliability doesn't suffice. Giving me coefficient alphas doesn't even come close to validating an instrument. A coefficient alpha tells me nothing about the validity.
Dr. Lohman said creating an instrument to answer your questions kind of like building your plane while you're trying to fly it. He says it's just...
It's a lot of work.
Yeah.
And students have done it. It's a lot of work. Because you know what, especially, what if you find the instrument doesn't work very well? What if you find your instrument ain't so hot and you want to use it in your research question? In other words, what if the factors and the items don't clump together nicely? What if the psychometric properties are low? Then you got a real problem. Because then you're going to be using, what?
Take your master's and run.
Take your master's, well then you're going to be using an instrument that you spent just tons of time creating and using a flawed variable in your predictive model. So you just run into a host of problems.
Why wouldn't you just create the item as your dissertation then?
But the thing is, in your proposal, you may have committed yourself to testing the research question.
Okay.
I mean, it is kind of like a contract.
Yeah.
What was your dissertation again?
My dissertation was looking at, we did a randomized experiment.
Workload.
Workload. The effects of qualitative and quantitative workload, which we manipulated, and its impact on stress and performance moderated by social support. So I did a kind of path analysis, MANOVAs, the whole repeated measures. We did it over 10 days. So it was a pretty complex study for way back then.
Yeah.
For way back. And we didn't know back then how to handle moderators and mediators in the same model. I asked that question back in the late, this is back in when SEM was still kind of new, and now we know how to handle models like that. So, which means you may have to look at exploratory or confirmatory factor analysis. Confirmatory is just really a much stronger form of evidence of your instrument. But let's say you have 25 items about attitudes in the workplace. Things like, I love my job, my boss is great. I seriously doubt you're measuring 25 unique and different phenomena. I doubt you're measuring 25 different constructs, 25 different domains. There's probably a few, 3 or 4 or 5. So that being said, everybody, exploratory factor analysis. Think of the word exploratory. It means you got 25 items and you're really not sure how they're going to cluster together. Maybe 5 items will measure organizational stress. Maybe 5 are about leadership. Maybe 5 are about teamwork. I mean, who knows? However, a much stronger stance is CFA, confirmatory. Here you're saying, I think these 5 items measure adaptability. I think these 5 measure organizational stress. I think these 5 measure vision. So here, confirmatory means you have an a priori hypothesis. But they are both types of tools to be able to ultimately reduce the dimensionality of this multi-item instrument. In other words, you have multiple items, and I guarantee you there's probably no way you're measuring 25 different things. There's probably no way. So it reduces the dimensionality of large number of variables to manageable number of dimensions, or factors, or categories, or clusters. People will use different vocabulary. I tend to use the term dimensions a lot. Some call it rubrics, some call it domains. There is a difference between factors and components, and I'm going to discuss that difference of a factor versus component. So you're at the initial stage of instrument development. And though you may think your project for HR is such that 4 items measure employee courtesy, 4 measure accuracy, 4 measure overall performance, how do you know that for certain? How many people have ever seen surveys and they have a big bold title, responsiveness, multiple items, right, accuracy, etc. How do you know that those items that purportedly are nested within these titles really measure that phenomenon? And what type of validity does this kind of seem to get at, everybody? You've had validity, right?
Yeah.
What type of validity? What I'm posing now, which form of evidence of validity does it seem to be getting at? Construct. And there's many ways to get at construct validity. There's many ways. Factor analysis is just one way. There's item response theory, generalizability theory. There's doing multiple groups, looking at group differences on constructs. Many ways to get at it. EFA and CFA are ways to be able to say, okay, I've got these items, and I think it measures a certain phenomenon. EFA is more exploratory. You're going to see that exploratory is kind of like what's called an unrestricted confirmatory factor analysis. You're going to see that it's unrestricted. You really aren't going to put in any prior information. Yes?
Just, this might be off topic, but it might not be. One of my psychometrics undergrad professor used IRT whenever he would give a test. He would announce, and then he would throw items out or keep items based on that.
Yeah.
Why do a lot of professors not do that? I mean, is it?
Well, because you have to have software to do it. I think the PAR program at universities does it, the Scantron. But basically, and I'm not going to get into this here. You're going to probably learn about IRT in your psychometric class.
She said she's not going to review it.
Oh, she's not?
And I remember thinking it was such a great tool, and I've not seen it since undergrad.
Ask her if she can do a little bit of time lecturing about it. Okay, because IRT is very important, and it's called modern test theory. And basically, you have this latent construct. It's called theta. Let's do it as a standard score from -3 to +3. Let's pretend this is math ability, which is a latent construct or a latent trait. And this is the probability of getting an item correct. Probability of getting an item correct from 0 to 100%. So this is item number 1. This is called the item characteristic curve. This is the item characteristic curve. And this shows at lower levels of ability, a lower probability of getting an item correct. As your ability increases, a higher. It takes on an S curve. It tends to have an S, or what's called a logistic curve, which is going to be perfect when we get to a logistic analysis, logistic regression. So basically what you can get at with item response theory, I can go ahead and look at theta minus the difficulty. Theta is your ability. This is what's called the difficulty of the item. Because items will vary. Think if you have an item like this. Why does everybody love that item?
It was easy.
Everybody got it right.
Too hard.
Yeah, right. Regardless of ability. So here, item response theory, as opposed to classical test theory, which just has one form of error, can take into account multiple dimensions, including ability, difficulty of the item, and slope of the item. That's called the two-parameter logistic model. Two-parameter logistic. So I can look at items and get a point-by-serial correlation for every item, see which item yields the biggest relation to the total score, and be able to prune that out and see which items are good. In fact, you can get some of this stuff from reliability. The item, have you gone over reliability in class? Have you analyzed data using reliability? You haven't. You're not analyzing data?
Well, I have, but we didn't do it in class.
Okay, because you could see there's the thing called the item total correlation, and that's the point by serial that you get in IRT. So IRT is incredibly useful in being able to take into account the latent trait of ability, difficulty of the item, the slope, and even, you can even add this third parameter model, which adds C. It's called a guessing parameter. This would be a weird one. Lower ability people have a higher probability of getting it right. So you get weird items like that. Means, guess what? There may be a guessing going on. So IRT is absolutely crucial for psychometric. There's more books about it now, more user-friendly books. Every psychometric book has a major chapter. I mean, and it's built in SEM programs now, structured equation modeling. So IRT has added a whole really critical toolbox for anyone versed in psychometrics. There's no way you can ever apply for a psychometric job and not have knowledge about IRT. That's just not going to happen. So I asked if she'll at least do so I can do this in half an hour. If she doesn't know IRT, have her give me a call. If my schedule permits, I'll come in and lecture to you guys for an hour. I did that for Ashley last year. Because a lot of people don't know this.
We're in class when you were teaching 6022.
Let's see if you want to stay an extra hour.
At 9 o'clock at night.
What's that?
I said 9 o'clock at night. I don't think that's going to apply.
You guys decide, but you guys need to know about it. You guys need to know about it.
Could you do 5 to 6? Or is that too early?
On Thursdays?
Yeah.
Yeah, I don't teach at San Diego State today. So yeah, I can. I really think you should have, I mean, I don't want to go on her turf, so you talk to her.
Okay.
If she has time, but you guys need to know about IRT.
Is that affected by sample size at all?
It's partially sample size also. Yes, in fact, that's why I've done it with 200-300 people, and sometimes the parameter estimates can be a little unstable. You know who created this stuff? The ETFs, Educational Testing Service. Do you think they have large databases? For the SAT, they have thousands and thousands. I mean, so yeah, it does like larger sample sizes.
So for a class of 5 people, it wouldn't work?
You mean if the sample size was 5?
Yeah.
No, it would work, but I wouldn't trust their estimates. So everybody, EFA is a great way to be able to see which items clump together, which dimensions. You see, I can have 4 items. I respond quickly to customer dissatisfaction. I respond nicely to customer dissatisfaction. I answer all customers' questions. I give correct answers. What is that measuring? So you got to give it a name. Part of EFA is giving it a name. See, CFA, you already have a name for it. You already have an idea what this construct is. What would you think that gets at?
Customer service ability.
Okay, customer service, possibly. But you don't know for certain unless you do your due diligence with psychometric testing. See, it's easy to create a job satisfaction or customer service scale. In SPSS, I could just sum them all up and create a sum score. It's easy to do. It takes you 2 seconds. But then, I'm still going to ask you, how do you know those 4 items measure customer service? Well, because we put them under a title like that. We've been doing that for years. That's our HR survey, our human resource survey for years. has created a score for customer service. But then I'm still going to come back at you and say, what evidence of validity do you have? Because remember, the definition of validity is evidence based on an inference from a score. And you're going to be getting a score for each individual. And that score better make sense, because maybe decisions are being made on this score. So, principle, we're going to talk about different types of rotations and different types of factors. This book gives a very, very brief rendering of EFA. If you have Grimm and Yarnold, hopefully you should read that too. This book is very slight. I used to get deep into all the mathematics of EFA. And if you want to take a look at it, I do have this right here, just if you're at all interested in the mathematics of it. I decided that's not as useful to people, but I've got everything drawn out here. It's kind of fun. It's in my handwriting. But it's all the mathematics, and it's a pretty dense terrain. You're going to get more the user-friendly use of EFA, but it's pretty dense. Really understanding EFA beyond the black books is fairly dense, so you'll get some of that. What you need to know, though, is the different types of rotations and extractions. In terms of the highlight, there are different ways when you get a solution to rotate. And what I mean by that is you may get a solution and a bunch of items cluster there, and they're not going to be very interpretable. And we're going to get into this. But soon, what if I rotate these vertices? What if I rotate these? See, some of these items, are they closer to the line now? Because I rotate. So you're going to learn there's different types of rotations to make your solution more interpretable. It's going to be easier to interpret. The second major decision to make is type of extraction. Because you're going to, do you think if I have 25 variable items on an HR survey, they measure 25 different things? Or do you think similar to what Zach was suggesting, maybe 4 measure customer service, maybe 4 measure responsiveness, right? Maybe 4 measure how to handle policy and procedures. Which means there's certain different types of statistical techniques to extract components. 2 of the major ones, and there's quite a few, are what's called principal components and principal access factoring, or what's often called as factor analysis. And I'm going to show you soon, it's called factor analysis. And look at the difference here, everybody. Principal components. Principal components, where Y is the principal component. It basically means the component is a function of the item and maybe a certain loading, like a regression coefficient. And this starts on the book on page 326. It's a linear combination. It's a linear combination of the variables. Look what's different with factor analysis. With factor analysis, here you actually have the item. The item, X, is a function of the construct or the component or the factor. In other words, everybody, principal components kind of looks like this. X1, X2, X3. Here's your individual items. I enjoy my job. I like coming to work. Work is good to me. And there I will just call this your component number 1. So that, do you see that that's a linear combination of the items? Factor analysis is very close to confirmatory factor analysis. Factor analysis, or principal access factoring as they call it in SPSS. Do you see here that the items are a function of the construct? Here's self-esteem, measured by 5 items. Here's depression, measured by 4 items. Here's impulsivity, measured by 3 items. So, principal access factoring, as a way to extract the factors, is such that the items are a function of the construct. Here, the component is a function of the linear combination of the variables. So the mathematics is slightly different for both of those. Now, the mathematics gets deep into eigenvalues, eigenvectors, and breaking down variance. You're going to learn how it breaks down variance. I'm not going to get into deep in the computation of eigenvalues. I'm going to show you a little of the math. But this really, if you remember early on, we discussed the importance of eigenvalues in matrix algebra, and this is when it comes into full bloom. So there's many, many decisions on types of extraction and rotation that you're going to use. That's why with factor analysis, some people call it part art, part science. A lot of decisions have to be made based on this. And it's really easy. It's really easy to use the default. But I'm going to show you why one should. So extraction is the mathematical approach to deriving the solution. PC means principal components. PAF means principal axis factoring. The ultimate corpus for analysis is the correlations of the items, meaning a correlation matrix. Correlation matrix. Though in CFA, you will be using the variance covariance matrix. So ultimately, you're going to use the correlation matrix, and you'll see when you get into this, everybody, you do analyze. It's under dimension reduction, because ultimately you're reducing the number of dimensions. Factor, and you put in your items. You put in your individual items right there, and soon you're going to see you have different options for extraction. You have principal components, principal axis factoring. There's quite a few. Those are the two main ones we'll focus on. Two types of extractions. And then you also have a lot of different types of rotations in SPSS. And there's more out there in the field. Here, a lot of times we use Verimax as the default, but I'm going to discuss Ultimate also. So here you see, there's actually quite a few decisions that I'm going to help guide you. What's nice is, with your psychometric classes, you're going to get this doubly reinforced. So this will be nice to get this doubly reinforced. Rotation. It's a geometric technique to make the factors, as I said, more interpretable. You literally are grabbing these vertices, right, and rotating them, and rotating them. Which means, initially, I have these items all over the place. Then if I kind of rotate it, the items will get closer to the vertice, and soon you're going to see the factor loadings that are produced will be more interpretable, will be much more interpretable. So, here's a factor analysis.
You're actually moving them on the grid?
Well, it's not so much the grid, but
Moving
mathematically.
grid.
Mathematically. You have these points, you have these items plotted in space, correlations, and you have the vertices that initially are just like this, right? Like little Cartesian coordinates. And using actually what's called sines and cosines in trigonometry, you can rotate them to make the loadings more interpretable. And soon you're going to see why it makes it more interpretable. So let's have item 9. Let's have 9 items, everybody, from the EFA. And look at the syntax, everybody. Here's your variables, criteria. We're going to learn soon what iterations means. We're going to use principal components for now. We're going to use the basic default that a lot of people use. And I always have people, whenever they submit an article, I say, what was your rationale for your principal components extraction and your Verimax rotation? And I'm going to discuss all of these. What is Verimax, everybody? So again, you go into Analyze, Dimension Reduction, Factor, Rotation. There's Verimax right there. There's Verimax rotation. What does Verimax mean, everybody? It's a type of orthogonal rotation. Do you recall what the prefix ortho had to do with? Right, yeah, right, uncorrelated, right angles. So you're going to create these multiple components that are uncorrelated. Multiple components that are uncorrelated. So the rotation, Verimax makes factors more interpretable. It cleans up the factors. And soon you're going to see why that's the case. See, you may have 25 items, but maybe there's 4 components. So you're going to have component 1, component 2, component 3. So you're going to find it cleans up the columns. You're going to get these things called factor loadings, which are very similar to what you get in discriminant function analysis. You're going to see a lot of parallels to this with discriminant function analysis. So what we want to do is the notion for EFA is that we have a linear combination of factors that are not actually observed. They're latent. Latent means it's unobserved. I don't know what depression is, or anxiety, or job sat. I really don't know. But I can ask an item. I feel satisfied on the job. I enjoy my job. Job is worthwhile for me coming to. And that's the way we make these constructs manifest. Manifest meaning somewhat observable, or as much as we can with the self-reporting inventory and all the deficiencies that come with it. So there are some differences, everybody, of principal components and factor analysis. Principal components, even though for SPSS we'll analyze correlation coefficients, it analyzes variances. It maximizes variance. Factor analysis analyzes covariance. And you're going to soon learn what communality means. It analyzes the shared information among the variables. Here, you're going to find that principal components, it analyzes all the variance, good and bad. Here, this only focuses on the good stuff. Principal components extracts maximum variance. The goal is to maximize the variance. You're going to generally find that you get a bigger R squared type of solution with principal components as opposed to principal axis factoring. Here, orthogonal components versus orthogonal factors when using Varimax. And you get a unique mathematical solution for principal components, but you don't with factor analysis. It's called the indeterminacy problem, where multiple solutions can potentially be derived. So there are some crucial differences theoretically and mathematically between these two. The fact is, you're going to run analysis on both of them, and usually they're going to be very similar. Usually you're going to get very similar results. So here are my items. Just 9 items. Here's the basic descriptive status. We're not going to get into missing data issues. There is a big problem. The default is list-wise deletion. The default is list-wise, and you have 146 people, but if all of a sudden 20 people have missing data on items, you're going to get all the way down to 123. So this is when you will want to avail yourself of the advances in missing data that is included both in SPSS, under its missing values module, or structured equation modeling programs, using either maximum likelihood or multiple imputation. You guys, I gotta warn you, if you do on your dissertation have missing data on some items, and it's inevitable, you got to address the missing data. If it goes from 146 to 123, even though you still have a nice sample size, it's not enough for you to say, well, I got 123, so I'm happy with that. Because I'm going to come back and say, yeah, but 23 are missing, and is there anything systematic that's unique about those 23 compared to the 123 that answered it that has an element of bias? So you've got to address missing data, everybody. So
what's better, the multiple imputation or the...
There's not one. A lot of times they give you similar results. Mm-hmm. If you look at my handout, the PowerPoint on missing data that I have, you'll see I compared them both. Sometimes they'll be very, very similar, so one is not necessarily better than the other. They're just slightly different. They're both excellent. I know that there is some research that shows at times multiple imputation. It doesn't recover parameter estimates, but I'm going to read one article and it seems it does a slightly better job under some circumstances, but they're both state-of-the-art. Both of those, maximum likelihood or multiple imputation. Now, rules of thumbs are a problem, and I've heard more than a few people, Tabachik, Fattel, or other books saying, well, what's my rule of thumb? Well, I should have 50 people is very poor, 100 is poor, 200 is fair, 300 is good, 500 very good, 1,000 excellent. Or I see things like 10 people per variable. I have 20 variables, I better get 200 people. You guys, there's enough articles out there on sample size factor analysis that shows that's not the case. Many things determine if you have an okay sample size. I've done EFA with as low as 100, and I know I've got a pretty good solution because my variable factor ratio is pretty good. My communalities, meaning percent of variance, is pretty good, which you're going to learn about. So a lot of things come into play, everybody, instead of these rules of thumbs, which means this article is called Sample Size and Factor Analysis. There's quite a few articles on it, but this is a 1999 Psych Methods article that shows what are some of the factors that one needs to consider for sample size. I will say, though, and I'm sure Don has emphasized this, generally for psychometric testing, the more you can get, the better. I mean, when my client says, how many should I get for, I want to do a full psychometric test of my instrument, and I do this for a lot of clients. I can say, well, how many do you think you'll be able to get? And if the sky's the limit, I'll say, then get the sky. If they say, Dale, at most I'll get 100, I go, well, we're going to be on the borderline if you have 80 items. So, especially with things like item response theory, especially with IRT. So then we're ultimately going to be analyzing a correlation matrix. For confirmatory factor analysis, you'll be analyzing the covariance matrix with variances on the diagonal, covariances on the off. Here, SPSS will use the correlation matrix. Sometimes looking at the easy stuff will shed insight into what's going on. If I have a small number of items, I can almost sometimes figure out how many factors will come out just by looking at the correlations. If I see a few have really big correlations and they're small with others, I know that one's probably going to cluster together. You can't see it from here, but you get this determinant. You get this determinant of the matrix. Remember, a determinant is a generalized variance. Remember, it's one number that captures an entire matrix. The determinant here is 0.051, and it's a determinant of a correlation matrix. So you have one number that encapsulates this entire matrix, and it multiplies all the eigenvalues. Soon you're going to see you get all these eigenvalues from the SPSS printout, and it basically multiplies all of them. And you hope that it's kind of small, because it means then there's a relationship. Now, if it's 0, you've got a problem. It means there's a linear dependency, which means the model is not called full rank. Full rank means there's a perfect overlap of 2 columns, and you don't want that. So ultimately, it tests this against a good old identity matrix, which again has 1 on the diagonals, 0 on the off diagonals. So that's just the determinant, one of the first things you get that not many people look at. Then you get this weird thing that you probably will never look at, called the inverse correlation matrix. Inverse R minus 1. And remember getting the inverse, everybody? Remember you had to divide by the determinant? Right, an inverse to do division, you had to divide by determinant. You can see you would never want to do this by hand. It's amazing. Cattell, some of those guys were doing this stuff by hand or electronic calculators way back in the 40s. I mean, this is stuff you need computers for. I have done some of the math for a few of the numbers in here if you want to look at it. But it's just, computers do it, but it's amazing they were doing this stuff by hand. But this is the inverse correlation matrix, which is used to derive what's called factor scores. Soon you're going to see the inverse times a factor loading is a factor score. A variable that can be used as a predictor. I don't use factor scores much, but I'm going to show you what they are soon. You also get this thing called the Kaiser-Meyer-Olkin test of sampling adequacy. Basically, there's no hard and fast rule. Tabachnik and Fidel say 0.9 or higher is fabulous. And they say 0.6 or higher is good. 0.791 is okay. Basically, it kind of takes into account, compares the magnitude of the observed correlations to the partial correlations. It approximates 1.0 if the partials are small. If the partials are small, that means there's not too much redundancy in your data set. So, you know, the bigger the better. I don't rely on it, and I don't get too worried about it. I really don't worry too much. Also, you get Bartlett's test of sphericity. Test of sphericity, as you recall, the correlations in a correlation matrix are 0. Test the correlations if they're 0. You want it to be significant, because if all your items have 0 correlations, that's not going to be a very fruitful solution, is it? If all 25 items have no intercorrelation, you got as many factors as you do items, which is not a very parsimonious way of capturing your instrument. Tabachnik and Fidel says this test is known as being very sensitive, and the use of the test is recommended only if there's fewer than 5 cases per variable, etc., etc. Here's the math. You will never have to worry about the math, but it's a chi-square test. It takes into account sample size -1, -2 times the number of items, plus 5 times 6 times the logarithm of the determinant of the correlation matrix. Can you see why you would want to do this stuff by hand often? But in case you were interested, here it is. We have 146 people, 2 times, we have 9 items, 5 times 6. Lord knows where Bartlett came up with 5 divided by 6. I mean, who knows? I mean, it's interesting how they come up with sometimes these constants. And I really would love to probably see that initial paper where he came with 5 divided by 6. There's that 0.051, which was multiplying all the eigenvalues to get at the determinant of the correlation matrix, 419.42. And looky here, everybody, 419.42. So there's the math that you probably never, ever, ever have to worry about. But it means that, you know what? There's a substantive relationship of the variables. If it wasn't significant, which I've never seen it, I've never done an EFA and the Bartlett's isn't significant. If it isn't, it means you must have a bunch of items that are just unique in their own right. So, you will never have to worry about this matrix. See, it gives you lots of matrices. It really spits out a lot. You will probably never have to worry about the anti-image matrix. It's the negative of the partial correlations. If I partial out the other variables, I can see what's left over. And if the proportion of partial coefficients are high, you may want to reconsider factor analysis. Why? Because it means that, guess what? They're not sharing much information. Because if I feel sad today, I feel hopeless today. Not bad, huh? You know they're kind of correlated? I see pink elephants on alternating Thursdays. Weird things fly over my head on Wednesdays. I punch roommates on Thursdays. Are there 3 items that maybe aren't so related with hopelessness and helplessness? I mean, maybe. But all of a sudden, if you have this anti-image where the partials are showing, guess what? There's not much shared information. You may want to reconsider it. So now you get one part that you will pay attention to. Communalities. This gets at the percentage of variance accounted for the item across all the components or factors contingent on which extraction method you're using. This means 77.8% of the variance in exercises, something I plan on my weekly schedule, is accounted for by the constructs. There may be 2 or 3 or 4. We haven't gotten to that yet. So communality, also called H squared, is basically the sum of the squared unrotated factor loadings. It's a percentage of variance explained for the item across the common factors. So this is a great first step for seeing if there's any problematic items. A lot of times people want to use factor analysis not only to get an idea of the structure of their instrument, but to see if they can prune it. Are there any items they can delete or omit? A lot of times people want to get an abbreviated version of their instrument. So here, if you find some of these have really low communalities, that might be a good starting place, maybe. Are any of them particularly low compared to others?
Yeah.
Which one?
4.
Okay, number 4, 0.588.
Right.
And 0.488. Do you see this one? I'm willing to change behaviors that are negative to my health.
Those 2.
Yeah, these 2. The rest are pretty good. The rest are pretty good. What is pretty good? If you go off this book, they say at least 0.6 and higher. Again, different opinions. 60% means 60% of the variance of the item is accounted for by that factors. Some are pretty darn high. 77.8 is the highest. I see a 76.6. I'm responsible for unhealthy habits in my life. So now you're getting a really good idea for how much the variance is accounted for. And how do you get at that, everybody? Soon you're going to find, not yet, do you see this thing called component matrix? 0.755 squared plus negative 0.369 squared plus 0.268 squared. It's going to give me 77.8. So it's the unrotated matrix, and it's just adding these squared factor loadings, which are kind of like a correlation of an item and the component. And doesn't this sound a little bit like a structure matrix in discriminant function analysis? So, when do I see red flags? Again, you guys, part art, part science. I can only tell you in my own work. If I see some that are 0.4-ish, 0.5, I'll take a look at the item. You know, again, I'd love to say, you guys, absolutely, if it's less than 0.5, get rid of the item. I'm not going to make that claim, because if you don't have a great factor analysis, a lot of them may be around 0.5. If you have a great one, they all may be greater than 0.6. So again, always look at it relative to the actual results of the instrument. But if it's less than 0.5, it means 50% of it is unexplained due to what's called uniqueness. I respond quickly to customer dissatisfaction. I answer all customers' questions. I give correct answers. I see pink elephants on alternating telecommutes. Is there an item that seems a little out of place? No, there isn't. So we got an h² of 0.23. So there's an item that I may want to go back on the drawing board, right? No need for unique factors if they include all items. What if one factor equals one item? It ain't much of a factor. So initial communalities when running an analysis for principal components is 1.0. The initial is 1.0. It starts off with 9 components, so to speak. But we're trying to reduce the dimensionality of it. And that's what principal components does, which you're going to soon see. So variability for an item is a function of communality plus uniqueness. And uniqueness can be even further divided to what's called specific variance and measurement error. So it's even further. So for item number 1 minus 0.778 means 22% is unexplained, unique. And uniqueness, everybody, can be further divided down. So total variance is h² plus u². Communality, shared among the common factors, uniqueness, and uniqueness can be due to specific variance and measurement error. Measurement error is things, right, flawed wording of the item, difficult, double-barreled, ambiguous. Specific may be variant to that item that's unique to that item. That's unique. It's not error, but it's unique to the item that's not shared with the other factors or items. That's just unique to that item that's not captured. So what you're soon going to find is principal components maximizes all this variance. All this. You're going to find factor analysis only looks at the shared. It only looks at the shared variance. It doesn't look at the error. So why don't we stop right here when we can get into the interpretation of the output from Verimax. This book does an okay job of EFA. I think the other one will shed even better insight. I'm not sure if you've been reading Grimm and Yarnall, but Grimm and Yarnall have a very nice one on EFA. And what I plan to do the next week is finish up the chapter on EFA. CFA will pretty much hold off on that until we get to structured equation modeling. So that's it, everybody. Take care. Have a wonderful week. Your homework is due next week on the one-way Mancova. And you take care now.